The emptiest space in the universe is not empty at all. Within a perfect vacuum, physicists have detected a ghostly push, an invisible force born from nothingness itself. This is the Casimir effect, a phenomenon where empty space teems with virtual particles that flicker in and out of existence. By the end of this, you will understand how measuring this almost undetectable force could redefine the future of physics. We will uncover why nothingness has energy and how this quantum secret might hold the key to the fate of the cosmos. What does true emptiness actually mean to you? For centuries, the idea of a perfect vacuum represented the ultimate emptiness, a space completely purged of every atom, every speck of dust, and every trace of energy. It was the scientific ideal of nothing, a pure and silent void. Classical physics painted this vacuum as a blank slate, an inert stage where matter could perform, but the stage itself was thought to be utterly still and passive. This conception of emptiness was straightforward, almost comforting in its simplicity, but then came quantum mechanics, and this comforting idea was completely overturned. The quantum world revealed that the vacuum is not a state of nothingness, but the lowest possible energy state a field can have, and this ground state is anything but quiet. Think of it like the surface of a still pond. To our eyes, it appears perfectly calm and flat, but if you could look at the molecular level, you would see a constant, seething turmoil of water molecules jostling and vibrating. The quantum vacuum is like that. Even at absolute zero, when all classical motion should cease, the void itself is alive with fleeting vibrations. These are quantum fluctuations, where pairs of virtual particles and antiparticles spontaneously blink into existence, borrowing energy from the universe for an impossibly short moment before annihilating each other and vanishing back into the background hum of spacetime. This redefinition is profound. True emptiness is not an absence, it is a simmering sea of potential, a dynamic arena where something is constantly happening. This fundamental shift in understanding did not remain a theoretical curiosity for long. It set the stage for a tangible, measurable force that would emerge directly from this restless nothingness, leading a brilliant mind to make a prediction that would forever change how we see the void. Hendrik Casimir's insight emerged not from pure abstraction, but from the gritty reality of industrial research. At the Philips Physics Laboratory in the Netherlands, Casimir and his colleague Hendrik were wrestling with a practical problem involving the forces between minuscule colloidal particles. Yet as he followed the elegant mathematics of quantum electrodynamics, his work took an extraordinary turn. He calculated that if you placed two perfectly smooth, uncharged metal plates within nanometers of each other in an absolute vacuum, they would be irresistibly drawn together. This was not magnetism, it was not gravity, this was a ghostly push from the void itself. Casimir realized the quantum field between the plates was being squeezed. The fluctuating sea of virtual particles can only exist in certain wavelengths, like notes on a vibrating string. Outside the plates, a full symphony of wavelengths is possible. But in the narrow gap, only specific, shorter wavelengths can fit, with more quantum activity pressing on the plates from the outside than from within. The net result is an inward push, a whisper of force born from pure geometry. At the time, this prediction was so subtle it seemed almost philosophical, a beautiful idea forever beyond measurement, but that whisper would soon demand to be heard. This constant, seething activity of the quantum vacuum is the engine that drives the Casimir force. To understand its fuel, we must go deeper into the fabric of reality as described by quantum field theory. Forget the universe as a collection of tiny, separate balls. Quantum field theory paints a far more fluid and interconnected picture. It proposes that the cosmos is fundamentally composed of fields, invisible entities that stretch across all of space. Think of these fields like an infinite, invisible ocean. The electromagnetic field is one such ocean, and what we perceive as a particle of light, a photon, is merely a ripple or wave on its surface. An electron is a localized excitation in the electron field. Everything is a vibration in its respective field. This perspective changes everything, especially our view of emptiness. According to QFT, these underlying fields can never be switched off. They are always on, and even in their calmest, most restful state, they are not truly calm. The vacuum is not passive. It is the lowest possible energy state of these fields, but it is a state of minimum, not zero, activity. This leads directly to the phenomenon of vacuum fluctuations. The Heisenberg uncertainty principle, a cornerstone of quantum mechanics, allows for a temporary loan of energy, so long as it is paid back almost instantly. The universe, it seems, runs on a form of quantum credit. This borrowing permits pairs of virtual particles and antiparticles to spontaneously erupt from the nothingness. They are not particles in the usual sense you can catch in a box. They are more like fleeting disturbances in the field, ghosts that appear for a sliver of a second before colliding and vanishing back into the background hum. You cannot see them directly, but you can see their shadow. It is like watching a pond on a windy day. You might not see the individual gusts of wind, but you can clearly see the ripples and waves they create on the water's surface. These virtual particles are the quantum gusts, and the Casimir force is one of the most profound ripples they produce. By connecting this to the metal plates, we see a beautiful convergence. The plates act like a filter for the electromagnetic field. Only certain vibrations, specific wavelengths, can fit and resonate in the narrow gap between them. The outside of the plates, however, allows for a full, unrestricted spectrum of these virtual fluctuations, with more quantum activity pushing from the outside than exists on the inside. The plates are gently squeezed together by the restless energy of empty space itself. The void is not empty, it is alive, and it exerts a whisper-soft touch. These virtual particles are the true ghosts in the quantum machine. They are not solid objects you could ever hope to hold. Instead, think of them as fleeting ripples in the fabric of reality itself, temporary disturbances in the underlying quantum fields that the universe is built upon. They are governed by a fundamental rule of quantum mechanics, the Heisenberg uncertainty principle. This principle allows for a tiny, momentary loan of energy, just enough for a particle and its antiparticle partner to blink into existence. The more energy they borrow, the shorter their lives must be, vanishing back into the void almost before they have even appeared. Picture the vacuum not as a still, black sheet, but as a frothing, effervescent sea. Virtual particle pairs are like the bubbles in that sea, constantly forming and popping in a frenetic, unending dance. You cannot capture a single bubble, but you can feel the fizz. And that fizz has real, measurable power. The subtle shift in the energy levels of hydrogen atoms, known as the Lamb shift, is a direct fingerprint of these virtual particles at work. Even the terrifying glow of Hawking radiation, theoretically streaming from black holes, is thought to be fueled by these quantum ghosts. But for our two metal plates hovering in a vacuum, the critical effect is a matter of space. The gap between the plates is so narrow it restricts which virtual photons, the particles of light and electromagnetic force, can appear there. Outside the plates, a full spectrum of these ghostly vibrations is allowed. This imbalance, with more activity pushing from the outside than exists within the gap, is what creates the palpable, squeezing force. These ethereal, temporary disturbances in nothingness manifest as a real, physical push, a direct pull from the empty room itself. This ghostly activity is more than just a curious trick of quantum mechanics. It hints at something staggering, a vast ocean of energy latent within every cubic centimeter of what we call empty space. The true magic of the Casimir force is not a push, but a squeeze. Picture two metal plates floating in a perfect vacuum, separated by a gap smaller than 1,000th of the width of a human hair. The quantum vacuum outside this gap is a chaotic free-for-all, a boundless arena where virtual particles of every conceivable wavelength can flicker in and out of existence. But the narrow gap between the plates is a different world altogether. It acts like a tiny, precise resonant cavity, a chamber that only permits specific vibrations. Only those virtual photons whose wavelengths fit perfectly within the gap are allowed to exist there. Imagine a guitar string. You can only play specific musical notes on it, notes that correspond to the string's fixed length. The gap between the Casimir plates works the same way, only permitting a select set of quantum notes to be played. The result is a dramatic imbalance. Outside the plates, an infinite symphony of wavelengths creates a constant, seething pressure. Inside the gap, only a limited, quieter ensemble is performing. With more quantum activity pressing from the outside than pushing back from within, the plates experience a net force that draws them irresistibly together. This is not because individual virtual particles are bumping into the plates like tiny billiard balls. The force emerges from the difference in the vacuum's energy density itself. The empty space outside is simply more energetically active than the confined space inside, and this gradient in the energy of nothingness manifests as a tangible, physical attraction. This elegant mechanism bridges a profound gap, transforming the most abstract principle of quantum theory into a force you could, in principle, feel with your own hand. It reveals that the geometry of emptiness itself can shape the physical world. Theorizing a ghostly force was one thing. Actually catching it was a battle against reality itself. Marcus Spanoi took up this monumental challenge in the late 1950s, attempting to transform Casimir's elegant mathematics into a physical measurement. His goal sounded straightforward: place two parallel metal plates just microns apart inside a high vacuum chamber and measure the infinitesimal pull between them. The reality was a nightmare of precision. The force Spanoi was hunting was almost unimaginably weak. For plates separated by 1 micrometer, the pressure amounts to the weight of a single tiny droplet of water, but distributed over an entire football field. Detecting this was like trying to hear a whisper in a hurricane. Every variable conspired against him. Minute electrostatic charges could generate forces millions of times stronger than the Casimir effect, completely drowning out the signal. A few stray gas molecules bouncing between the plates would mimic the very force he was trying to find. Even the simple heat in the room, causing the metal to expand and contract, created enough thermal noise to obscure the quantum whisper. Spanoi's initial results were messy, burdened with enormous error margins and lingering doubts. Yet within that frustrating data was a glimmer of something profound. His painstaking work, published in 1958, provided the first rough, hesitant confirmation that Casimir was right. It was not a triumphant announcement, but a hard-won foothold. Spanoi's struggle proved that measuring almost nothing was one of the most difficult tasks in all of physics, setting a daunting standard for anyone who would follow. His perseverance opened the door, and a new generation of scientists was ready to step through with tools of even greater sensitivity. Spanoi's difficult work demanded a new approach, a way to sidestep the maddening precision required by two perfectly parallel plates. The solution was a stroke of geometric genius. Instead of a second plate, physicists introduced a smooth spherical lens. This single change was a revolution in measurement. With a sphere facing a flat surface, the critical alignment problem evaporated. A microscopic tilt that would have ruined a parallel plate experiment now had a negligible effect because the sphere only makes near-perfect contact at a single tiny point. The force was still vanishingly small, but the mathematics for this new geometry was far more manageable, and the physical setup was infinitely more stable. The true breakthrough came in 1997, when physicist Steve Lamoureux used this very method. He suspended a spherical lens above a flat plate using an exquisitely sensitive torsion balance, a device that could measure twists caused by forces smaller than the weight of a single bacterium. As he brought the sphere and plate within nanometers of each other, the Casimir force pulled them together, causing a minute but definitive rotation in the balance. This was no longer a shadowy signal buried in noise. It was a clean, direct observation of the quantum vacuum's push. The sphere-plate geometry had finally pinned down the ghost, providing unambiguous proof that empty space itself could exert a force. This was the turning point where a brilliant theoretical prediction became a hard, measurable fact of physics. With the Casimir effect now firmly in their grasp, researchers could begin to ask deeper questions, probing how this force behaves when they change the very rules of the void itself. Even the most perfect vacuum is never completely cold. The metal plates used to measure the Casimir force exist at room temperature, and this warmth introduces a second, ghostly actor onto the stage. To isolate the pure quantum whisper, scientists had to learn to distinguish it from the constant murmur of heat. At absolute zero, the force is a clean signature of the quantum vacuum, a product of virtual particles alone. But at any real-world temperature, the plates themselves radiate a soft glow of thermal photons. These are real photons born from heat, and they also exert a pressure on the surfaces. For gaps smaller than a micron, the fierce quantum Casimir force reigns supreme. But as the separation widens, the story changes. The thermal contribution, once a faint background hum, begins to swell. At larger distances, it can actually become the dominant force pulling the plates together, a thermal echo mimicking the quantum effect. This delicate dance is captured by a more powerful theory developed by Evgeny Lifshitz. His framework elegantly weaves together both the quantum fluctuations of the vacuum and the thermal fluctuations from heat, providing a complete picture of the forces at play in the void. Precisely subtracting this thermal component became the next great challenge in measurement. It revealed that what we call empty space is not one force, but a conversation, a subtle interplay between the restless energy of the quantum world and the familiar warmth of our own. This thermal quantum duality means that to truly hear the voice of the vacuum, you must first learn to quiet the heat of the world. And once scientists could do that, they began to wonder if they could not just measure this ghostly force, but actually command it. But the story of the Casimir force holds a stunning twist, one that upends everything we thought we knew about the push of nothingness. For over half a century, the dogma was absolute. The Casimir effect was always attractive, an inevitable pull drawing objects together in a vacuum. This seemed like an unbreakable rule of the quantum world. Then theorists like Ivar Breivik began to ask a dangerous question. What if it was not a rule, but merely a common outcome? Their mathematical explorations revealed a breathtaking possibility. Under very specific conditions, the ghostly force could reverse, becoming a repulsive push. The secret lies in the electromagnetic personalities of the materials involved. Every substance interacts with the quantum vacuum's fluctuations in a unique way, a property known as its permittivity. For a repulsive force to emerge, you need a precise cocktail of materials. Imagine a gold plate and a plate made of silica like pure glass. Now, instead of a vacuum, immerse them in a special fluid like bromobenzene. In this delicate arrangement, the contributions from the different frequencies of virtual particles no longer work in unison. Some push, some pull. Critically, because of the specific permittivities of gold, silica, and the fluid, the pushes can begin to outweigh the pulls. The result is a net repulsive force. The empty room in this specific configuration is no longer squeezing things together. It is holding them apart. This discovery transforms the Casimir force from a simple quantum curiosity into a potential tool. It opens the door to a phenomenon that sounds like science fiction: quantum levitation. Imagine a nanoscale gear in a tiny machine, suspended in nothingness by the repulsive push of the quantum vacuum itself. Without any physical contact, friction would vanish. The relentless, whispering pressure of empty space could become the ultimate non-contact bearing, allowing unimaginably delicate machines to operate with perfect smoothness. This counterintuitive push reveals that the quantum vacuum is not a monolithic entity with a single will. It is a nuanced and complex participant, capable of both a ghostly handshake and a firm, ethereal stop sign. This ghostly push from the void is no longer just a physics curiosity. It has become a formidable engineer in the world of the infinitesimally small. Inside micro-electromechanical systems, or MEMS, and their even smaller cousins, NEMS, the quantum vacuum holds real power. These are the machines that run our world unseen, the accelerometers that tell your phone which way is up, the tiny mirrors that project light in digital projectors, and the minuscule switches that route information at the speed of light. Their gears, levers, and cantilevers are so small that the gaps between them are measured in nanometers. At this scale, gravity is almost irrelevant. But the Casimir force is not. It becomes a dominant player, a phantom grip that can slam moving parts together and lock them in place permanently. Engineers call this devastating failure stiction. A switch designed to flip millions of times can suddenly freeze, its motion halted by the relentless, silent pressure of empty space itself. The very phenomenon that fascinated physicists has become a nightmare for nanotechnologists. They cannot ignore the void. Instead, they must design around it, choosing specific materials with just the right electromagnetic properties or sculpting components into clever geometries that subtly frustrate the vacuum's attractive pull. They are learning to negotiate with nothingness, yet this same force, once tamed, offers incredible promise. Visionary researchers are not just trying to defeat the Casimir effect. They are asking if they can recruit it. Could we design a nanoscale bearing where a repulsive Casimir force levitates a component, eliminating friction entirely? What about a quantum ratchet, a device that uses the asymmetric push and pull of vacuum fluctuations to drive a tiny rotor in one direction, harvesting energy from the seemingly empty space around it? The force that once threatened to break our smallest machines could one day become the engine that powers them. This is the ultimate lesson. A deep secret of the cosmos, hidden in plain sight, has stepped out of the theoretical realm and into our practical reality, proving that the quantum whisper of the vacuum speaks directly to the future of our technology. Yet this whisper of a force points toward a cosmic scream. The energy density of the quantum vacuum, so vividly demonstrated by the Casimir effect, connects directly to the greatest unsolved problem in all of physics. This is the mystery of the cosmological constant. In his theory of general relativity, Albert Einstein introduced this constant as a kind of fudge factor. a repulsive energy inherent to space itself that could keep the universe from collapsing under its own gravity. He later called it his greatest blunder, but modern science has brought it back from the dead. We now know the expansion of the universe is accelerating, driven by a mysterious dark energy. The most straightforward candidate for this dark energy is the energy of the quantum vacuum itself, acting as Einstein's cosmological constant. Here is where the crisis erupts. Physicists can calculate how much energy the quantum vacuum should contain. They sum the contributions from every possible quantum fluctuation, from every field, across every conceivable wavelength. The number they get is monstrous. It suggests a vacuum energy so unimaginably dense that the universe should have ripped itself to shreds moments after the Big Bang. The observed value of dark energy measured from the expansion of the cosmos is different. It is not just a little bit smaller. It is 1 followed by 120 zeros times smaller. This is not a small error. It is the single worst prediction in the entire history of science. How can our two most successful theories, quantum mechanics and general relativity, be so catastrophically wrong about the energy of nothing? The Casimir effect is our only tangible grip on this problem. It is one of the very few ways we can actually probe and measure the properties of vacuum energy in a laboratory. Every precise measurement of the Casimir force is a data point in this grand cosmic puzzle, a test for any new theory that dares to explain why the void is not boiling over with power. The gentle push between two metal plates in a silent vacuum chamber is a direct conversation with the fate of the entire cosmos. It forces us to ask what we are missing. Is there a hidden symmetry that cancels out most of this vacuum energy? Are we misunderstanding the nature of gravity on cosmic scales? Or does the answer lie in realms of physics we have not yet even imagined? The empty room holds a secret that could rewrite our understanding of everything. Casimir's elegant model of perfect metal plates had one beautiful flaw. It was too perfect. In the real world, no material is a flawless conductor at all frequencies, and laboratories are never at absolute zero. The whisper of the quantum vacuum had to be heard through the noise of real materials and everyday warmth. This is precisely where Evgeny Lifshitz stepped in, delivering a far more powerful and complete theory in 1956. Lifshitz provided the master key. His framework did not just describe an idealized scenario. It calculated the force between any two real material bodies by diving deep into their unique electromagnetic personalities. The secret lies in a property called permittivity. Think of permittivity as a material signature, a measure of how it responds to different colors of light, even the invisible colors we cannot see. Every substance, from gold to glass to water, has its own distinct permittivity profile across the entire spectrum of frequencies. Lifshitz's genius was to weave these unique signatures directly into the calculation of the quantum force. His formulas show that the Casimir effect is not a one-size-fits-all phenomenon. The strength of the attraction, and even the possibility of a repulsive push, depends entirely on the electromagnetic dance between the specific materials involved and the fluid that might surround them. This is why a gold plate and a silica plate immersed in bromobenzene can experience a repulsive force. Their permittivities, combined with that of the fluid, create a situation where the vacuum's push overcomes its pull. Furthermore, the Lifshitz theory seamlessly incorporates the effect of temperature. It recognizes that the heat radiating from the plates themselves emits real photons that contribute their own pressure, a thermal force that becomes significant at larger separations. This is the full picture. The ghostly force is not just a product of an abstract empty space. It is a dialogue between the restless quantum void and the tangible, imperfect matter within it. Lifshitz gave us the language to understand that entire conversation, transforming a theoretical ghost into a predictable, measurable reality. With this complete theoretical toolkit in hand, the stage was set for a new kind of exploration, one that would manipulate the quantum vacuum itself. But what if the walls of this empty room could move? The static Casimir effect reveals a force from a still vacuum. Introduce motion, however, and the phenomenon transforms into something even more spectacular. This is the dynamical Casimir effect, where the quantum vacuum is not just squeezed but shaken. Imagine a mirror, not a normal mirror, but one that can vibrate impossibly fast, its surface oscillating at a significant fraction of the speed of light. According to quantum theory, this furious motion does something extraordinary. It can rob the virtual particles flickering at the edge of existence of their borrowed energy, but instead of vanishing, they become real. The mirror's acceleration acts like a cosmic pump, converting the vacuum's ghostly fluctuations into tangible, detectable photons of light. It literally shakes particles into reality from nothingness. This is not just a theoretical fantasy. In 2011, a team at Chalmers University of Technology in Sweden achieved this incredible feat. They did not use a literal piece of glass moving at relativistic speeds. Such a thing is mechanically impossible. Their genius was to use a superconducting quantum interference device, or SQUID. By modulating a magnetic field, they made this SQUID act like an electrical mirror for microwaves, one whose effective surface was vibrating at a breathtaking 25% of the speed of light. And from that artificially churning vacuum, they detected something unmistakable. Real microwave photons emerged, particles of light that had been coaxed out of the void. This was a direct observation of the dynamical Casimir effect. The line between the virtual and the real had been blurred in a laboratory. This discovery shares a profound kinship with Hawking radiation, the theoretical glow from black holes, where the immense gravity at the event horizon is thought to perform a similar trick, plucking real particles from the quantum foam. The dynamical Casimir effect brings that cosmic drama down to Earth, proving that motion itself can be a source of creation, pulling real light from the seeming darkness of empty space. This ghostly handshake from the void reaches down to touch the very building blocks of matter. Just 1 year after his initial prediction, Hendrik Casimir, now collaborating with Polder, realized the force that bears their names was not confined to metal plates. It operates on a far more fundamental scale, in the intimate space between a single, neutral atom and a surface. This is the Casimir-Polder force. Imagine a lone atom hovering near a perfectly smooth wall. According to classical physics, with no charge and no chemical bonds, there should be no force between them. They should ignore each other completely. But the quantum vacuum forbids such indifference. The atom itself is not a static, solid ball. It is a dynamic cloud of electrons, a tiny antenna constantly broadcasting and absorbing its own faint electromagnetic fluctuations. These are the atom's personal quantum whispers. When this atom approaches a surface, its electromagnetic field is disrupted. The wall acts as a mirror for the virtual photons the atom is constantly exchanging with the vacuum. Some of the wavelengths the atom prefers to emit are suppressed, no longer fitting the new geometry imposed by the nearby boundary. This distortion creates an imbalance in the quantum pressure surrounding the atom. With more virtual activity pushing it from the side away from the wall than from the side facing it, the atom experiences a net force pulling it toward the surface. For an atom in its ground state, this is always an attractive force, a gentle but insistent tug from the wall. The strength of this tug is not constant. It changes dramatically with distance. Extremely close to the surface, it is fierce, pulling with a force proportional to the inverse fourth power of the distance. As the atom moves farther away, the force softens, eventually weakening to an inverse seventh power dependence. This delicate dance is not just a theoretical curiosity. It governs whether an atom will stick to a surface or bounce away, a process crucial to chemistry and material science known as adsorption. In modern laboratories, where scientists use intricate patterns of light and magnetic fields on microchips to trap and manipulate ultra-cold atoms, the Casimir-Polder force is an unavoidable reality. It can subtly shift the energy levels of these trapped atoms or even pull them out of their carefully constructed cages, ruining an experiment. By studying this force, physicists are not just observing a quantum effect. They are conducting a profound test of quantum electrodynamics in an environment dominated by a boundary, pushing our most precise theory of light and matter to its limits. The whisper that draws two plates together is the same whisper that guides a single atom, proving that the quantum vacuum connects the vastness of the cosmos to the spin of an electron. Even with our most advanced tools, the quantum whisper remains maddeningly difficult to hear. Modern experiments pushing for ultimate precision face a gauntlet of microscopic imperfections that can completely distort the signal. The central challenge is creating a surface that is perfectly smooth, an ideal that does not exist in our rough world. The Lifshitz theory assumes two flawlessly flat planes. But real metal, even polished to a mirror's shine, is a rugged landscape of hills and valleys when viewed at the atomic scale. A bump just a few nanometers high, a mere 10 atoms wide, acts like a tiny mountain range. When two such surfaces are brought within nanometers of each other, these peaks make contact long before the valleys do, dramatically changing the true average separation and throwing off the force calculation entirely. It is like trying to measure the precise gap between two sheets of sandpaper pressed together. The microscopic hills bear all the pressure while the deeper valleys are untouched. Scientists must therefore not only measure the force, but also meticulously map the topography of their surfaces with atomic force microscopes, building a three-dimensional model of the roughness to subtract its confounding effect from the quantum signal. This battle against the grain of reality itself is just the first obstacle. To even begin the subtraction, you need to know exactly who is dancing with the vacuum. The force depends intimately on the materials involved, defined by their permittivity across a vast spectrum of frequencies. This is the material's unique fingerprint, a complex profile of how it responds to every possible color of light, from radio waves to extreme ultraviolet. A slight error in this fingerprint, especially in the critical infrared range where thermal effects live, creates a domino effect of inaccuracy. The theoretical prediction from Lifshitz becomes unreliable, and the beautiful agreement between experiment and theory shatters. Researchers spend as much time characterizing their materials with precision spectrometers as they do measuring the force itself, and then there is the ever-present phantom of electrostatics. Even the most neutral surfaces can develop tiny patch charges, localized areas of positive or negative static that generate forces millions of times stronger than the Casimir effect. To exercise this phantom, experimenters use a clever trick. They apply a small, carefully calibrated voltage bias between the surfaces. They sweep this voltage until the electrostatic force cancels itself out, finding the precise point of zero potential. Only in this quieted electrostatic field can the true quantum force finally emerge from the silence. As if this were not enough, when the surfaces get incredibly close, almost touching, our very description of matter begins to fray. The Lifshitz theory treats materials as a continuous substance, a smooth electromagnetic fluid. But at sub-nanometer separations, the discrete, grainy nature of atoms becomes impossible to ignore. Effects called spatial dispersion and non-locality mean that the material's response to the vacuum's fluctuations at one point depends on what is happening at another point. The simple picture breaks down. To overcome these layered challenges, physicists are turning to ever more ingenious methods. They use custom fabricated probes on atomic force microscopes, their tips engineered into perfect spheres or flat paddles. They conduct experiments at cryogenic temperatures, chilling their apparatus to within a few degrees of absolute zero. This deep freeze subdues the thermal vibrations of atoms, quieting the thermal noise that can mask the quantum signal. Each of these techniques is a testament to the extreme sensitivity required to probe the quantum vacuum. This is not merely measurement, it is a high-wire act performed at the limits of physics, where every atom, every stray charge, and every degree of heat must be accounted for in the quest to listen to the voice of nothingness. The quantum whisper grows louder when the metal itself begins to sing. Beneath the smooth surface of a material like gold, a hidden dance is taking place. Electrons are not sitting still. They are engaged in a collective sloshing motion, a rhythmic wave that pulses across the metal's boundary. These are surface plasmons, coordinated oscillations of the electron sea, and they hold a surprising key to the strength of the Casimir force. For idealized perfect metals, the force is a simple story of confined wavelengths. But for real metals, the plot thickens dramatically. The energy of the quantum vacuum is not spread evenly across all frequencies. It has peaks and valleys, and surface plasmons create a massive peak. They act like a powerful, resonant antenna tuned to a specific note, absorbing and emitting virtual photons with extraordinary efficiency. When two metal surfaces are brought close, their individual plasmonic tunes do not just play side by side. They interact, coupling together to create a new, shared electromagnetic duet. This coupling dramatically reshapes the landscape of possible vibrations in the gap. It funnels a huge portion of the vacuum's energy through this resonant channel, amplifying the force far beyond what a simple model would predict. At certain intermediate distances, this plasmonic contribution can become the dominant voice in the quantum chorus, responsible for most of the attractive pull you measure. This discovery transforms the force from a fixed law of nature into something that can be designed. If surface plasmons control the strength of the interaction, then by engineering those plasmons, we can engineer the force itself. This is the frontier of active Casimir control. Researchers are now creating metamaterials, artificial substances with structures finer than the wavelength of light. By carefully designing these nanostructures, they can craft materials with bespoke plasmonic resonances. Imagine a surface etched with billions of tiny pillars or holes, a landscape designed to make the electron sea dance to a specific tune. With such a material, you could, in principle, dial the Casimir force up or down. You could even create a situation where the force does not simply pull, but oscillates between attraction and repulsion as the distance changes, like a ghostly spring. This is no longer passive observation. It is a conversation with the vacuum, a direct manipulation of nothingness using the hidden rhythms of the electron world. We are learning to compose the symphony of empty space. If you thought the Casimir effect was strange, wait until you hear its theoretical cousin. In 1990, physicist Klaus Scharnhorst made an astonishing calculation. He proposed that the speed of light itself is not an absolute constant. Inside the narrow gap of a Casimir cavity, sandwiched between two perfect metal plates, a photon traveling parallel to those plates would not move at its usual universal speed limit, c. It would move ever so slightly faster. This is the Scharnhorst effect, a mind-bending consequence of the altered quantum vacuum. The logic follows directly from the Casimir setup. We know the space between the plates has a lower energy density than the outside vacuum. In quantum field theory, this energy density is tied to the vacuum's refractive index, a measure of how much it slows light down. A lower energy density means a lower refractive index. In the open vacuum, the refractive index is exactly 1, but inside the cavity, Scharnhorst showed it dips just below 1. Light, therefore, faces less resistance and accelerates by a minuscule amount. The sheer tininess of this effect is difficult to overstate. For plates separated by 1 micrometer, the increase in the speed of light is estimated to be about 1 part in 10 to the power of 30. That is a decimal point followed by 29 zeros and then a 1. Detecting this is so far beyond our current technology, it is practically a philosophical point. And crucially, this is not a crack in the foundation of relativity. You cannot use this trick to send information faster than light and violate causality. The Scharnhorst speed boost only applies to light traveling along the plates, perpendicular to the force. To send a signal, you would have to get the light into the cavity and then back out again, and that round trip would always take longer than light traveling the same distance through the normal vacuum. So causality remains safe, but the profound implication remains. The ultimate cosmic speed limit appears to be not just a property of empty space, but a property of a specific kind of empty space. By placing boundaries on the void, we can, in theory, change the very rules of the game. The Scharnhorst effect suggests that spacetime itself is not a static stage. It is a dynamic medium, and its most fundamental properties can be bent by the ghostly presence of nothing at all. The gentle push between 2 metal plates echoes across the cosmos. This tiny force in a vacuum chamber is a whisper from the same source that screams through the expanding universe. We call this source dark energy, the mysterious agent accelerating the growth of space itself. The cosmological constant, once Einstein's discarded fudge factor, is now our best description for this relentless push. Its measured value, while unimaginably small, is the single most important number for our ultimate fate. Everything hinges on this faint energy of nothingness. Will the universe continue to expand at an ever-increasing rate, stretching galaxies so far apart that the night sky becomes utterly black and cold? Could this vacuum energy grow stronger over time, eventually overpowering all other forces in a catastrophic big rip, shredding galaxies, planets, and even atoms themselves? Or is there a chance, however slim, that this energy might one day reverse its sign, pulling the universe back into a fiery collapse? The Casimir effect is our only tangible handle on this cosmic mystery. It allows us to probe the properties of vacuum energy right here on Earth, in a controlled laboratory setting. Every precise measurement of the force between those plates is a direct test of the physics that governs the entire cosmos. This creates a staggering paradox. When we sum all the quantum fluctuations in the vacuum, we calculate a vacuum energy so colossal it should have annihilated the universe instantly. The actual observed value is 120 orders of magnitude smaller. This is not a small error. It is the most profound discrepancy in all of science. Why is the universe not boiling over with this latent power? What subtle symmetry or unknown principle cancels out almost all of this energy, leaving behind just the faintest whisper we detect as dark energy? The answer is hidden in the geometry of empty space, in the subtle dance between virtual particles and boundaries. By studying the ghostly handshake in an empty room, we are not just exploring a quantum quirk. We are reading the first few lines of the universe's final chapter. The ghostly force first predicted by Hendrik Casimir now has its own legacy etched in scientific history. His name is bestowed upon one of the most respected honors in the field, the Hendrik B.G. Casimir Award. This prestigious prize celebrates the pinnacle of research in quantum electronics and quantum optics, disciplines that live and breathe the phenomena Casimir helped uncover. It is a direct tribute to how one man's curiosity about nothingness rippled outward to shape entire frontiers of science. The recipients of this award are the modern explorers of the quantum realm. Their work often builds directly on the foundation Casimir laid. Many laureates have made groundbreaking advances in cavity quantum electrodynamics, a field that studies how light and matter interact within confined spaces. This is the direct intellectual descendant of Casimir's two plates. They are mastering the art of trapping single atoms and individual photons, orchestrating the very dance of virtual particles and light that gives rise to the Casimir force itself. These scientists are not merely observing the quantum whisper, they are learning to conduct its symphony. The award underscores a profound truth, a seemingly obscure prediction about an almost imperceptible force in a vacuum was not an end point. It was a seed. That seed has blossomed into a vibrant, growing field that continues to challenge our understanding of reality. It inspires each new generation to probe deeper into the counterintuitive quantum world, to ask what other invisible forces are hiding in plain sight, waiting for a brilliant mind and a sensitive enough experiment to reveal them. This ghostly push from the void forces us to ask a question that physics alone cannot answer. What does it mean for something to be real? Virtual particles are not real in the way a table or a planet is real. You cannot trap one in a box or see its trajectory. They are evanescent, more like a mathematical possibility than a solid object. Yet their effect is undeniably physical, a measurable force that moves metal plates. So where does that leave them? Are they merely a convenient fiction in our equations, or do they represent a deeper layer of reality, one that is fundamentally probabilistic and fleeting? This touches on a core philosophical puzzle known as ontology, the study of what truly exists. The classical view of reality was built on certainty and direct observation. If you could not see it or touch it, it was not truly there. The quantum vacuum shatters that intuition. It suggests that what we call reality is just the stable, observable tip of a vast, churning iceberg of potential. The vacuum's energy is not a mathematical trick. It is a physical actor that curves space-time and dictates the fate of the cosmos. The Casimir effect is our proof. When we measure that gentle pull between two plates, we are not just collecting data. We are conducting a profound experiment on the nature of existence itself. We are proving that the universe is built not on a foundation of static objects, but on a seething ocean of probability and relationship. The line between what is real and what is potential becomes blurred, revealing a world where existence is a spectrum, not a binary state. This shifts the very goal of physics. It is no longer just about cataloging what is there, but about understanding the latent power of what could be. The empty room is not empty. It is a plenum of potential, and its quiet hum is the sound of reality being forged from nothingness. The same quantum whisper that pulls at metal plates in a lab has also captured the imagination of storytellers. You can find the ghost of the Casimir effect haunting the pages of science fiction novels and the blueprints of theoretical starships. In these fictional worlds, the vacuum energy is not a subtle force. It is often portrayed as a roaring river of power, a source of limitless free energy waiting to be tapped. Writers dream of Casimir-powered engines that could propel ships across galaxies without fuel or exotic devices that create force fields by manipulating the fabric of empty space itself. These stories tap into a powerful human desire to find a key to the universe's hidden vault, to unlock the potential energy seething just beneath the surface of reality. The idea of getting something from nothing is intellectually intoxicating. It resonates with age-old themes of alchemy and magic, but dressed in the language of modern physics. This cultural footprint, while often scientifically fanciful, serves a vital purpose. It acts as a gateway, translating an impossibly complex quantum principle into a narrative of adventure and discovery. A viewer might first hear about virtual particles in a show about a starship's warp drive, and that spark of curiosity could lead them to the real and even more fascinating science. Of course, this creative license comes with a trade-off. The fictional versions almost always grossly overstate the effect's strength and accessibility. Harvesting usable net energy from the Casimir effect with our current understanding is a physical impossibility, a dream of perpetual motion cloaked in quantum terminology. The force is real, but it is also conservative. The energy you might extract by allowing plates to come together is exactly equal to the energy you had to expend to pull them apart in the first place. There are no free lunches, even in the quantum vacuum. Yet, this gap between science fiction and scientific fact is not a failure. It is a testament to the power of a profound idea. The Casimir effect has become a cultural symbol for the untapped potential of the quantum world, fueling our collective dreams of what might lie just beyond the edge of our current technology, in the quiet, energetic depths of the empty room. The future of the Casimir force lies in our ability to command it. Rather than just observing this ghostly push, scientists are now designing ways to turn it on and off, or even reverse its direction with the flip of a switch. The dream is to use external magnetic or electric fields to actively tune the properties of materials in real time. Imagine a nanoscale device where applying a small voltage instantly changes the electromagnetic personality of a surface, switching the Casimir force from a firm pull to a gentle push. This would be the ultimate form of control over the quantum vacuum, transforming it from a fixed background actor into a dynamic tool for nanotechnology. Such active control could prevent the stiction that locks tiny machines, or even enable frictionless bearings that levitate components on a cushion of nothingness. The geometry of the void itself is also being reimagined. Researchers are moving beyond simple plates and spheres to explore corrugated surfaces etched with intricate patterns. These are not smooth mirrors, but landscapes of microscopic ridges and grooves. In these complex structures, the quantum vacuum does not just create a straightforward pull. It can generate lateral forces, sliding components sideways along the surface, or even inducing a torque, a twisting motion born from pure nothingness. This opens the door to vacuum-driven nanoscale motors, where the restless energy of empty space performs actual work. The quest for precision is pushing measurements into new territories. Can we detect the Casimir force not just at nanometers, but at micrometer distances where thermal effects dominate? What happens in complex fluids or at temperatures near absolute zero? Each new condition is a rigorous test for the Lifshitz theory, probing whether our fundamental understanding of the quantum vacuum holds true or if it begins to crack, revealing new physics. Underpinning all this applied research is the grand, unresolved mystery of the cosmological constant. Every precise measurement here on Earth is a data point for the cosmos, a clue to why the energy of the vacuum we measure in a lab is so vastly different from the one that drives the universe's expansion. The manipulation of empty space in a chamber is a direct conversation with the nature of dark energy. We are not just building better machines, we are learning to compose symphonies with the quantum vacuum, and the first few notes suggest the void has melodies we have not yet begun to hear. The art of measuring nothing demands tools that border on magic. Optical tweezers are one such instrument, using the gentle pressure of a tightly focused laser beam to grasp a microscopic particle and hold it suspended in mid-air. This is not science fiction. It is a standard laboratory technique that allows scientists to manipulate a single, tiny sphere of glass or plastic with nanometer precision. To measure the Casimir force, researchers use this laser trap to position a particle exquisitely close to a flat surface. As the ghostly pull of the quantum vacuum tugs the particle toward the surface, the laser trap must work slightly harder to hold it in place. This minute change in the laser's force provides a direct, exquisitely sensitive readout of the Casimir interaction. The beauty of this method lies in its inherent cleanliness. Because the trapped particle is dielectric and electrically neutral, it is far less susceptible to the phantom forces of stray electric charges that have plagued earlier experiments. The particle can also be kept slightly farther from the surface, reducing the nightmarish complications of atomic scale roughness. It is a quieter, more refined way to listen to the quantum whisper. In another corner of the lab, a different kind of cold is revealing the same force. Scientists are now using clouds of atoms chilled to within a millionth of a degree of absolute zero. At these temperatures, the atoms lose their individual identities and merge into a single quantum wave, a Bose-Einstein condensate. This ultra-cold blob of matter is the most pristine and well-controlled object imaginable. By bringing this condensate close to a specially engineered chip surface, physicists can study the Casimir-Polder force with unbelievable accuracy. They can watch as the quantum vacuum gently distorts the shape of the atomic cloud, measuring the attraction with a precision that was once a fantasy. These are not just incremental improvements, they represent a fundamental shift in the quest. We are no longer just trying to detect the force. We are using perfectly controlled quantum systems to interrogate it, to ask whether our theories, like Lifshitz's framework, hold true in every detail. Any tiny discrepancy between prediction and measurement could be a crack in the foundation, a hint of a new force or a new particle influencing the void. These advanced techniques are the new high-precision microscopes trained on emptiness itself, transforming the art of measuring almost nothing into a science of profound exactitude. The quantum whisper is not confined to still rooms. Its voice changes depending on who is listening, or more precisely, how they are moving. This brings us to a profound companion of the Casimir effect, known as the Unruh effect. It proposes that an astronaut accelerating at a tremendous rate through the seemingly empty void of space would not find silence. Instead, their rocket ship would be enveloped in a warm glow of real particles, a thermal bath heat where an observer floating at a constant velocity would perceive only an absolute and frigid vacuum. This is not a malfunction of the ship's sensors. It is a fundamental feature of reality. Both the Casimir and Unruh effects spring from the same stunning realization. In the quantum world, a particle is not an absolute thing. Its very existence depends on your frame of reference. The concept of a particle is a matter of perspective. In the Casimir effect, the perspective is set by static boundaries. The metal plates redefine the vacuum, creating a new reality where the force emerges. In the Unruh effect, the perspective is set by motion. The accelerating observer's own journey through space-time constantly splits their past and future horizons, effectively creating a boundary in time that makes the vacuum appear to boil with real particles. One effect sculpts the vacuum with walls, the other sculpts it with motion, yet both reveal the same underlying principle. The quantum vacuum is not a static backdrop. It is a fluid, dynamic stage, and what we see on it depends entirely on how we are positioned upon it. Our measurement is not a passive act of reading a pre-written script. It is an active participant in the play, changing the lines and the characters simply by how we choose to observe. This deep connection is a cornerstone for any unified understanding of quantum fields, whether they are confined between two plates or stretched across the vast, curved spacetime of a black hole or the early universe. The empty room and the accelerating rocket are telling us the same story. Reality is a conversation, and the quantum vacuum always answers in the voice of the person who asks the question. But behind the elegant certainty of the equations, a quiet debate simmers about what this force truly represents. The mainstream story tells us the Casimir effect is a direct manifestation of vacuum energy, the ghostly push of virtual particles. Yet a compelling alternative viewpoint argues this interpretation is a kind of beautiful illusion. Physicists like Robert Jaffe at MIT contend that the force can be explained without any reference to the metaphysical energy of the void. In this picture, the Casimir force is not fundamentally quantum in nature. It is an amplified version of the van der Waals force, the same kind of attraction that makes geckos stick to walls or causes individual molecules to weakly attract one another. The metal plates are not being squeezed by the vacuum. Instead, the force emerges from the dance of charged particles within the materials themselves. The electrons in one plate are constantly jiggling, creating fleeting positive and negative regions, or dipoles. These fluctuating dipoles induce mirror fluctuations in the electrons of the second plate. The resulting correlated dance creates a net attraction, a simple, if complex, electromagnetic handshake between the atoms in the two solids. So where do the virtual particles go? In this interpretation, they are not physically real. The mathematics of quantum field theory, with its virtual photons and zero-point energy, is seen as an incredibly powerful and convenient calculation tool, but not a literal description of reality. It is the difference between a map and the territory. The map, filled with symbols for virtual particles, gets you to the right destination, but the actual journey is across the real landscape of correlated atomic dipoles. This debate cuts to the very heart of how we interpret quantum mechanics. Are vacuum fluctuations a physical substance, a churning sea of potential that truly exists, or are they merely a computational artifact, a mathematical fiction that happens to yield the correct answers? For all practical purposes, the predictions are identical. An engineer building a nanomachine does not care which story is true. The device behaves the same way. But for a physicist seeking to understand the fundamental fabric of reality, the distinction is everything. It asks whether the most counterintuitive aspect of quantum theory, something from nothing, is actually built into the universe or is just a feature of our description of it. This ongoing conversation proves that even a force we can measure with exquisite precision can still hide profound mysteries about the nature of existence itself. Even the most ethereal quantum whisper can be brought down to earth with the right analogy. To understand the strange push of nothingness, picture a quiet harbor on a calm day. Out in the open sea, waves of all sizes and wavelengths roll freely across the surface. This endless, chaotic sea of waves represents the full spectrum of virtual particles allowed in the unconfined quantum vacuum. Now imagine two long, parallel piers jutting out into this water. In the wide open water beyond the piers, every possible wave can still exist, but in the narrow channel between them, only specific waves can fit. Just as a guitar string only supports certain musical notes, the gap between the piers only permits waves whose wavelengths divide evenly into that confined space. The result is a dramatic imbalance. The unrestricted sea outside pushes with the full force of its countless waves, while the restricted channel between the piers pushes back with only a limited set. The piers are squeezed together by the sheer pressure differential of the water itself. This is the heart of the Casimir effect, translated from the quantum realm to a scale we can intuitively grasp. Of course, the real force is not about water waves, but the fundamental fluctuations of space-time. A direct macroscopic demonstration is impossible because the Casimir force is a uniquely quantum phenomenon. Yet, scientists have created ingenious analog systems that mimic its behavior. In laboratory dishes, researchers confine fluids or liquid crystals between two boundaries. Just as the quantum vacuum seethes with virtual particles, these fluids are filled with thermal fluctuations, tiny, random jiggles of molecules driven by heat. When the boundaries are brought close together, they restrict which types of fluctuations can exist in the gap. This alteration in the spectrum of these thermal waves generates a measurable, attractive force between the surfaces, a classical echo of the quantum original. These educational models are more than just simple illustrations. They are vital tools that demystify one of physics' most counterintuitive ideas, transforming an abstract equation into a tangible principle about how boundaries shape the invisible activity around us. By making the strange familiar, these demonstrations unlock the door for new minds to step through, inspiring the next generation to listen more closely to the hidden symphonies of empty space. This relentless pursuit of a quantum whisper has quietly revolutionized the world of precision engineering. The tools forged in the crucible of Casimir research have become indispensable in high-tech industries, transforming abstract physics into tangible economic value. Consider the semiconductor industry, the bedrock of modern computing. To etch circuits smaller than a virus onto a silicon chip, manufacturers must position components with nanometer accuracy. The very same ultra-sensitive force sensors and piezoelectric positioning stages developed to measure the Casimir effect are now deployed on fabrication lines, ensuring that these billion-dollar machines operate with flawless precision. A single misalignment, smaller than the width of a DNA strand, can render an entire microchip useless. The battle against stiction in nanomachines directly informed the design of anti-stiction coatings now used in accelerometers for airbags and smartphones, preventing these microscopic components from permanently locking up. This is not a mere trickle-down effect. It is a direct pipeline from the frontiers of fundamental physics to the factory floor. In biotechnology, the atomic force microscope, an instrument refined through decades of probing quantum forces, allows scientists to map the topography of a single protein or to observe molecular interactions in real time. This capability is accelerating drug discovery, enabling researchers to design medications that fit into biological targets like a key in a lock. The deep understanding of van der Waals and Casimir-Polder forces, honed in vacuum chambers, now guides the creation of new materials. Engineers designing next-generation adhesives, which must stick powerfully yet release cleanly, rely on this knowledge. The development of superlubricants, where surfaces slide past one another with almost zero friction, draws directly from our comprehension of how atoms interact at the closest possible range. The quest to measure nothing has, paradoxically, given us unprecedented control over something. It has built a foundation for the entire nanotechnology revolution, proving that the most profound questions about the universe often yield the most practical answers for our world. Our journey through the secrets of the empty room reveals a universe where nothingness is the most active participant. From Hendrik Casimir's elegant prediction to the delicate dance of modern experiments, we have felt the ghostly push of the quantum vacuum, a force born from the silent, seething energy of space itself. This is not merely a scientific curiosity. It is a fundamental key to reality, bridging the infinitesimal quantum realm with the vast destiny of the cosmos, reshaping our technology and challenging our very philosophy of existence. The Casimir effect forces us to abandon simple intuition, proving that the universe is far stranger and more magnificent than we ever conceived. The exploration of this ethereal frontier is only accelerating. As we refine the art of measuring almost nothing, we are not just closing a chapter, we are opening a new one, asking what other profound whispers are waiting in the quiet. If this journey to the edge of nothing has sparked your curiosity, there are countless more cosmic mysteries waiting to be uncovered. We invite you to subscribe and continue exploring with us, and we would love to hear your thoughts on these ghostly forces in the comments below.